Welcome to this lecture on Solutions to Exercise 5.2, Question 1 to Question 8 by Dr. Rajesh Singh.
Welcome everyone to this lecture series. Today we are going to solve exercise for section 5.2 from the book Introduction to Real Analysis by Bartle and Sherbert. So let us start with the first question. So the first question is, this is the first question. We have to determine the points of continuity of the following functions, and we have to also mention the results that we have used in each of this case. Okay, so if you look at the first function, so when you look at the first function, it is nothing but, if you see, the numerator is also a polynomial and denominator is also a polynomial. So fx is a rational function, and we know that every rational function is continuous on its domain, and since the denominator is nowhere 0, so it is continuous everywhere on R. Since every rational function is continuous on its domain, every rational function is continuous on its domain, and the domain of the function f is R of the rational function f is R. So this implies f is continuous on R. Fine. Now let us take the b part. So b part is gx is equal to root x plus x. So this is a combination of 3-4 functions. So let us take the first function. So let fx equal to x for all x belonging to R. This is defined on whole R, and take hx equal to root x, and this is defined for all x greater than equal to 0. So we know that f is continuous on the R being the function fx equal to x, and h is continuous on the set R positive union 0, set of all positive real numbers and also including 0. So it is continuous for all x greater than equal to 0. So this implies your f plus h by algebra of limits, the function f plus hx, which is equal to fx plus hx, which is equal to x plus root x, is continuous on R plus union 0, right? Because h is continuous on this set and f is continuous on whole of R, so together they are continuous on this set. And again, when you will apply, so g is nothing but, since g is equal to h of f plus h x, and composition of two function is continuous, and composition of two continuous function is continuous, hence g is continuous on R plus union 0, the set of all non-negative real numbers. Okay, so you can represent h, because g is nothing but this h of f plus h, right? Now third, what is the next part? We have to show that hx is equal to, so third part, we are given hx equal to root 1 plus mod sin x upon x, and x is not equal to 0. So we have to define 3-4 functions again. The first function is sin x, so f1x is equal to sin x, f2x, you can, because mod is also used, so mod x. So this is defined for every x in R, this is also defined for every x in R. Then because 1 plus something is there, so f3x is 1 plus x for every x in R, and then you have another function here, so it will take f4x equal to x. Okay, for this is also defined for every x in R, and they all are continuous for every x in R, right? And finally we have this function, okay, root is not in the whole of x, so this is okay, and this is f5x, you have to take root x, and this is defined for all x greater than equal to 0. Okay, so now h can be written as, so h is nothing but your function f5 of, so then you have this combination of, so this is f3 of, and then f2 and f1. Okay, so this is how this your function is defined, f3 of f3, so this x. Okay, so this is your numerator, and then denominator is f4x. So we have to, so now we have to discuss the continuity of these functions, and we know that f1 is continuous, so f1 to f4 they are all continuous for every x in R. So we know that f1, f2, f3 and f4 are continuous on R, and f5 is continuous on R plus union 0. Now because this f1 is continuous on R, so by composition of, and f2 f4 1 is also continuous, because composition of two for continuous function is continuous, then again because composition of two continuous function is continuous, so this f5, although it is continuous only on R plus union 0, but because this function is continuous on R and its range set is the set of all positive real numbers, so this function is continuous on the domain of this function, right? So it is continuous on whole of R. So f3 of f2 of f1 is continuous on R, since composition of two continuous function, is continuous. Okay, so this is continuous on R, and your, and f5 is continuous on R positive union 0, and range of f3 of f2 of f1 is R positive union 0, is a subset of this. Exactly we don't know, so we can call it as subset of this. So this implies f5 of composition of f3 composition f1 is continuous on whole of R, because we know that GOF is if continuous on domain of F, provided F is continuous on its domain and range of F is contained in domain of G. So because of this, the theorem that composition of two continuous function is continuous, this is continuous on R, so your whole this function H, this is continuous on, and now denominator is defined for every x not equal to 0. f4 is defined, so this by quotient rule, so by algebra of continuous functions, sorry, So by algebra of continuous functions, h equal to f3 f5 of f5 of f3 of f2 of f1 by f4 is continuous on r minus 0, because this function f4 is 0 at 0, so that's why we have to remove this point, except at all other points it is continuous. Now let us take the fourth part. This is kx equal to cos root 1 plus x square. So here we have three functions. So first is cos x, then we have root, and then we have 1 plus x square. So kx is a combination of three functions. So kx is equal to cos of root 1 plus x square. So f1x, define f1x equal to cos x. This is defined for every x in R and is continuous on R, right? And f2x equal to root x. This is defined for all x greater than 0 and is continuous on R positive union 0. And then f3x equal to 1 plus x square. This is defined for all x in R and is continuous, being a polynomial. Now kx is cos of this. So kx k is equal to your f1 of f2 of f3, f1 of f2 of f3, and you can see here 1 plus x square is always positive, so range of f3 is contained in f2. f3r is contained in a domain of f2, which is r positive union 0, right? And range of f2 of f3 is obviously, because its domain is full R, so this is, so hence, so since composition of two continuous function is continuous, so f2 of f3 is continuous on R also, as f1 is continuous on R. So this implies k, which is equal to f1 of f2 of f3 is continuous on R. Okay, so composition function gof is continuous on domain of f, provided its range is contained in the domain of G. Otherwise we will have to check where these are defined, right? So this is question number 1. So we have completed question number 1. So let us move to question number 2. So in question number 2, so this is the question number 2. We are given a continuous function f defined on A, and n is any positive, n is any natural number, and the function fn is defined as fnx equal to fx to the power n. We have to show that it is continuous on A. So this can be shown by using the fact that pointwise product of two continuous function is continuous, and then inductively we can use that result to get this result. So let us try this. So we are given f is continuous on A. To show fn is continuous on A, so we will use principle of mathematical induction to prove this result. Okay, so we will prove it by induction. So for n equal to 1, it is trivially true. For n equal to 1, fn is equal to f and is continuous on A. So we are done in this case. Okay, so assume that the result is true for n equal to k, that is fk is continuous on A. Claim, so to show claim result is true for n equal to k plus 1. So we have to show that it is true for n equal to k plus 1, that is to show fk plus 1 is continuous on A. Okay, and this can be done as, since fk plus 1 is equal to fk dot f, pointwise product of f, pointwise product. So so this product fk is continuous on A, f is continuous on A. So by algebra of continuous function, where we know that product pointwise product of two continuous function is continuous, by algebra of continuous functions, fk plus 1 is continuous on A. Okay, so second, so since the result is true for, so by principle of mathematical induction, fn is continuous on A for all n belonging to n. So we have completed question number 2 also. It was simple. We used the principle of mathematical induction. Now let us move to the third question. So in the third question, we are asked to give an example of functions f and g that are both continuous at a point C in R, such that the sum f plus g is continuous at C and the product fg is continuous at C. So we have to define two functions f and g that are both continuous at a point C in R, such that the sum is continuous at C and the product fg is continuous at C. So proof, you can take the Dirichlet functions both f and g, where you can take, let define fx equal to 1 if x is rational and 0 if x is irrational, and define g to be opposite of this. So gx equal to 0 if x is rational and 1 if x is irrational. Then your f and g are discontinuous everywhere on R. So हमें तो एक पॉइंट पे शो करना था. We have got two functions which are discontinuous everywhere on R. And now what you can do is, you can now f plus g x is equal to fx plus gx, which is equal to 1 plus 0 if x belongs to Q and 0 plus 1 if x belongs to Q complement, so which is equal to 1 for all x belonging to R. So f plus g is a constant function, and fgx is equal to fx dot gx, which is equal to 1 dot 0 if x belongs to Q and 0 dot 1 if x belongs to Q complement. So this is nothing but the constant function 0 for every x in R. So hence both f plus g and fg being constant functions are continuous everywhere on R. This is how you can take an example. So this is one simple example which you could have considered for this. So although we were asked to prove at a point, we were able to prove on the whole set R. Okay. Now let us take the question number 4. So this question is related to greatest integer function. The similar questions that we did in exercise 5.1. So again, so in this question we are given the greatest integer function. So we have to determine the points of continuity of the function fx equal to x minus this greatest integer function of x. So we know that the greatest integer function is discontinuous at continuous on at non-integers, right? So greatest integer function is continuous at non-integers, and this function is continuous everywhere. So fx will be continuous, definitely will be continuous on non-integers. We just have to check its continuity at the set of integers. So fx is equal to x minus mod x for all x belonging to R. Claim f is continuous on R minus z, only on R minus z, and discontinuous on z. So only on R minus z, set of non-integers. So let C belongs to R be any real number. We will show that if C is so case 1, C belongs to R minus z. So we have to show that the function is continuous at this point. So we will take any arbitrary epsilon. So let epsilon greater than 0 be any real number. Okay. So C is this. Consider fx minus fc. So this is your x minus x minus c plus c. So now what we will do is, whenever we have this greatest integer function of this type, so because c is a real number, it is not an integer, so mod c will be smaller than c, and this will be mod c plus 1 will be bigger than c, because c is non-integer, so it will lie between these two consecutive integers, this greatest integer function of c and this. So what we will do is, we will try to choose a delta such that c minus delta lies between this, so that if we pick any x belonging to this, then value of that will also be mod this greatest integer function of c. So for that, what we will do is, we will choose let delta equal to minimum of c minus greatest integer function of c and c plus 1 minus c. So we are taking this distance, and minimum of the two, and then, or you can put 1 by 2 also for being on the safer side. So then for any x belonging to c minus delta to c plus delta, mod x is greatest integer value of x is equal to the greatest integer value of c. So from star it follows that fx minus fc will be equal to this x minus mod c minus c plus c, so which is equal to x minus c. So if we take, so we have to take, okay, sorry, we have to take delta equal to minimum of these two, and as well as epsilon. Okay, so we have to include the epsilon also here. So then by this choice, because delta is minimum of these two, delta is less than epsilon, so x minus c less than delta will imply, so this is less than equal to delta, and which is less than epsilon, which is equal to which is less than equal to epsilon by 2, which is less than epsilon. Hence fx minus fc is less than epsilon whenever your x minus c is less than delta. Hence f is continuous at x at c. Now case 2, when c is integer, then you take two sequences as we always do in the case of greatest integer function. So let xn equal to c plus 1 by n and yn equal to c minus 1 by n for all n belonging to n. Then for this sequence, f of xn is equal to xn minus xn, which is equal to c plus 1 by n minus c plus 1 by n, and because c is an integer, so this is equal to c plus 1 by n minus c for all n greater than equal to 2. For n equal to 1, this will become c plus 1, which is again an integer, so we exclude the case when n equal to 1. So this is equal to 1 by n, so f of xn converges to 0. Now what about f of yn? F of yn, if you take f of, so n greater than equal to 2, so f of yn is equal to yn minus this, which is equal to c minus 1 by n minus c minus 1 by n, which is again equal to c minus 1 by n minus c plus 1. So this will become, so again for all n greater than equal to 2, because for 1 again this will become an integer, so we want to exclude that point. So this will become c minus 1 minus c will cancel out, 1 minus 1 by n, and this converges to, so f of yn converges to 1. So since, so we have got two sequences, so by divergence criteria for continuity, f is not continuous at c, because we are able to construct two sequence both converging to c, xn and yn both are sequence converging to c, but their corresponding sequence fxn and fin converging to different limits, so f is not continuous at c. So hence from the two cases we conclude that f is continuous only on r minus z. Now let us take the next question, which is question number 5. So in this we are given the function g from r to r defined as, so g is defined as gx is equal to 0 if x is equal to 1 and 2 if x is not equal to 1. So g is not continuous at x equal to 1. Yes, because it is taking different value, limit value is 2 while the value of the function at g is equal to 1. So this is not continuous at x equal to 1, and we are given the function fx equal to x plus 1 for all x belonging to r. So this is continuous everywhere on r. To show limit x tends to 0, g of f is not equal to g of f 0. Claim limit x tends to 0, g of fx is equal to 2 is not equal to g of 0. So this, because this is defined like this, so let x and so this we can do in two ways. We can use the sequential criteria for limit, or we can use we can use epsilon delta definition. G of f0 is equal to g of f0, which is equal to g of 0 plus 1, which is equal to, now what will be this, g of 1, and g of 1 is defined to be 0. So we have to show, so limit is not equal to 0, that is what we have to show. So to prove that, we have to find some epsilon, such that if we take any delta greater than 0, then corresponding to that we will be able to find some x, such that g of fx minus g 0 is greater than epsilon. So we can take epsilon equal to 1. So let epsilon is equal to 1, and let delta greater than 0 be any real number. Okay, so we have to, so let x equal to delta by 2 belonging to minus delta, 0 minus delta to 0 plus delta. Then consider g of fx minus 0. So this is nothing but, so g of fx is g of delta by 2 minus 0. So this is nothing but g of 1 plus delta by 2 minus 0. Now 1 plus delta by 2 is greater than 0. Yes, so greater than 0, so delta by 2 is greater than 0, so 1 plus delta by 2 is distinct from 1, so it will be 2 minus 0, so which is equal to 2, which is greater than epsilon equal to 1, right? So hence for this epsilon corresponding to this epsilon equal to 1, we are able to find, so if we take any delta, then corresponding to that we will be able to find a point x equal to delta by 2, such that this is greater than epsilon. So this implies f limit x tends to 0, g of x is not equal to 0, which is equal to g of 0. And why this is happening? Although if you see, this is so if the limit were equal, then the function would have been continuous at x equal to 0, but because the value of the function at 0 is 1 and g is discontinuous at 1, so that's why this is failing to hold. We have been asked that why doesn't this contradict theorem 5.2.6. In theorem 5.2.6 it is given that composition of two continuous function is continuous, although the function g is continuous at 0, but it should be continuous at the point fc. Let us look at the statement of the theorem 5.2.6. So if you look at the statement of the theorem 5.2.6, so this is the statement of the theorem 5.2.6, and why does this example does not contradict this? So it does not contradict this because, so here if you can see, f be two functions such that f is contained in B and f is continuous at point C, so f is continuous at C and g should be continuous at fc, then g of f will be continuous at C. So if, so because this f of 0 is equal to 1 and g is not continuous at x equal to 1, that is at f of 0, so that's why this example is not contradicting this theorem, right? Because g is continuous at 0, but when we talk about composition, we talk about the composition continuity of f at c and g at fc, so that's why it is not contradicting the statement of the theorem, because it is not satisfying the statement of this theorem. Okay, so this implies G and F does not satisfy the hypothesis of the theorem 5.2.6 at x equal to 0. So it fails to satisfy the hypothesis, and therefore the result may or may not hold. So in this case it is not holding, so therefore it is not contradicting this statement. Okay, let us take the next question, which is question number 6. So in this question we are given two functions f and g and a point c belonging to R. We are given that limit x tends to c, f is equal to b and g is continuous at b. So limit is existing at x equal to b, the limit of the function is existing. So we have to show that limit x tends to c, g of f equal to gb. So let us start. So what we are given two things. Limit x tends to c, fx is equal to b, and second, g is continuous at b. And claim limit x tends to c, g of f equal to g of b. So we have to show limit x tends to c, g of f equal to g of b. So for this, to show this, so this, if in fact if we will just repeat the proof of theorem 5.2.6. so if you will repeat the proof of theorem, so instead of using the continuity part, we will use that limit x tends to c, fx is equal to b. So that is why you can have this function. So you can just repeat the proof, or let us just write the proof. So let epsilon greater than 0 be any real number. So we start with any epsilon greater than 0, then we use the continuity of g. So since g is continuous at b, so for above epsilon greater than 0 there exists delta star. So we will be getting another delta, so that's why we are taking it delta star greater than 0, such that g of y minus gb is less than epsilon whenever y minus b is less than delta star. Y minus b is less than delta star, so mark it as 1. Now as limit x tends to c, fx is equal to b, so instead of using epsilon we will use this delta star. So for delta star greater than 0 there exists delta greater than 0, such that it is totally the same proof which we did for this theorem, composition of two functions, such that fx minus b is less than epsilon, less than delta star whenever, so now because we are using the definition of limit, so whenever x minus 0 is less than x minus c less than delta. So we have to exclude the point x equal to c. So we are excluding the point x equal to c here. Here we have not excluded the point y equal to b, but here we will exclude the point x equal to c. So fx minus b is less than delta star whenever 0 is less than x minus c less than delta. So then now for any x belonging to c minus delta to c plus delta and x, or for any x such that 0 is less than x minus less than delta. So from 2 what we will have fx minus b is less than delta star using second. Okay, because x satisfies this property, so from second this property is satisfied. Now fx minus b is less than delta star, so fx is in place of y, we can put fx, so fx is satisfying this condition, so in place of y we can put fx here. So this implies g of fx. So in place of y we are putting this gfx gb is less than epsilon using 1. Okay, because fx is satisfying this property, fx is satisfying the property of 1, hypothesis of 1, so this will hold, and hence g of fx minus gb is less than epsilon whenever 0 is less than x minus c less than delta. So by definition of limit x tends to c, g of fx is equal to gb. So this is the proof is similar to what we did for composition of two functions, but there we were given f is continuous at c, but here we are given the limit point of f. So that's why we are able to we have excluded the point when x is equal to c here, and here we had to show just the limit of this. Okay, so this completes question number 6. Now let us take the question number 7. So we have to give an example of a function that is continuous at every point of 0, 1. Give an example of a function that is discontinuous at every point, but its modulus function is continuous. So again, you can take the Dirichlet function, because Dirichlet function is discontinuous everywhere, and so you have to define d equal to, so define f from 0, 1 to r as f of x equal to 1 minus 1 if x belongs to q intersection 0, 1, and if x belongs to q complement intersection 0, 1. Then we know that f is discontinuous, you can easily prove it also, everywhere on 0, 1. And what about mod f? Mod fx is equal to mod of fx, which is equal to 1 for all x belonging to r. So mod f is a constant function, so since mod f is constant on r, so this implies mod f is, sorry, on r3 we have to define on the interval 0, 1, so we are talking only on 0, 1, so we just need to talk on 0, 1. So f is continuous on 0, 1. Okay, so this completes your question number 7. Now let us take another question, which is question number 8. So this is also a simple question. So we have already done such type of questions where we were given to show that if f of x is equal to 0 for every rational, then and the function is continuous, then f of x is 0 for all r. That what we did a similar question for this. So it is similar to, let me show you the question. So it is similar to this question which we did in exercise 5.1. If you see this question, so this question we did in exercise 5.1, so it is similar to that. So we can use this result also. F is continuous, fr is 0 for every rational number, prove that fx is equal to 0. So what we can do here is, we can let h equal to f minus g on r. Then clearly h is continuous on r by algebra of continuous function, right? Because some difference of two continuous function is continuous by algebra of continuous function. Also hx is equal to, for every x in q, for all x in q, hx, which is equal to fx minus gx, is equal to 0, since fx equal to gx on q, right? On q they are same, so it is 0. So h is equal to 0 on rational and h is continuous. So from this, from the question, yeah, from the result it follows, that hx is equal to 0 for all x in R. So you can repeat the proof of this. There is alternate proof for this, which you can have a direct proof for this. So direct proof is similar to what we did for this. So again we take any sequence. So let's see so we have to show that fx is equal to gx for every x belonging to q. So given fg continuous on R, and second f is equal to g on q. To show, we have to show f is equal to g on R. So we pick any, because it is already equal on q, so we pick any irrational number. So let c belongs to R minus q. So we pick any irrational number and we will show that fc is equal to gc. So now because this belongs to q, so by density theorem we will have, by density theorem there exists a sequence xn in q such that xn converges to c, because this sequence will converge to c. Now by sequential criteria for continuity, now since f is continuous, fg are continuous on R, since fg are continuous at c, so by sequential criteria for continuity, so by sequential criteria for continuity, fxn will converge to fc and gxn will converge to gc. Now for all n belonging to n, f of xn is equal to g of xn, since xn belongs to q. So this implies limit n tends to infinity f of xn is equal to limit n tends to infinity g of xn, and this implies fc is equal to gc, because the limit is fc and its limit is gc. So fc is equal to gc. So since c belongs to R minus q is arbitrary, it follows that fc is equal to gc for all c belonging to R minus q, and this implies fx is equal to gx for every x in R, because we have already shown that, we are already given that fx is equal to gx on q, and we have shown that fx is equal to gx on R minus q. So fx equal to gx on complete R. So I take a break here. In this part in this part of the video I will solve till question number 8, and from the next part, in the next part of this lecture series, we will solve from question number 9 to question number 15. So thank you everyone, have a good day.
Thank you for watching this video. Please subscribe to our YouTube channel, Online Learning, to stay updated and share with your friends. Happy learning through online learning. To watch more, click on any of these cards. Thank you once again.